This video is an introduction to summary statistics. What are statistics? Statistics are the collection and evaluation and interpretation of data. Data being any kind of points or measurements that you've taken on something, say, such as an experiment. Why are statistics important for us as future engineers? That's because statistical analysis of measurements can help verify the quality of a design or a process. You can verify using numbers that this is a good solution to your problem using statistics. There are several kinds of summary statistics. The average value of a variable, like rainfall depth, is one type of statistic that indicates central tendency. It gives an indication of the center of the data. For example, averages, or also known as the mean. The median and mode are two other indications of central tendency. Central meaning sort of like the middle. But often we need more details on how much a quantity can vary. Statistical dispersion is the variability or spread of the data, so how far the data varies from this middle number or mean. The range, standard deviation, and interquartile range are indications of dispersion or variability. Even more detail about a variable can be shown by a frequency distribution, which shows a summary of the data values distributed throughout the range of values. Frequency distributions can be shown by frequency tables, histograms, box plots, or other summaries. The mean is the most frequently used measure of central tendency. You may also know this as the average. It is strongly influenced by outliers, which are very large or very small data values that do not seem to fit with the majority of the other data points. To calculate the mean, you use the formula on this page. The mu means mean value. Then this is the summation. This is a sigma, Greek letter sigma, and it means summation or add them all up. X sub I means the individual data value, so take each individual value and add them up. And then the N means the number of data values in your set. How many data values did you add? That's the number you're going to divide by. Let's look at this example data set. If I wanted to find the mean of this value or the average of this set, then I would first add up all of the values. So when I add 3, 7, 12, 17, 21, 21, 23, 27, 32, 36, and 44, I come up with 243. If I counted how many points, how many data points there are in this set, I find there are 11. So when I follow the formula, I take the sum of all of the points, 243, and I divide by the number of points, which were 11, and I get 22.09. Now we've talked a little bit about significant figures in the last lessons, and now I want to show you how this works with rounding in statistics. As a general rule, do not round until the final answer. If you're writing intermediate results on your paper, you can write rounded values, but you need to keep the unrounded number in your calculator's memory and use it until you get to the final answer. For the average or the mean, you need to round to one more decimal place than the original data. So let's take a look at what we just calculated. Our mean came up to 22.09. When I look in my original data set, I had whole numbers. So I'm going to round to one more decimal place than what I had in the data set, so I'm going to give one decimal place. So my final answer is going to be 22.1. In this case, the result of the mean calculation is 22.09, with the 09 repeating. That's what the bar above the 09 means, is repeating. Keep this number saved in your calculator if you need it for future calculations, such as the standard deviation, which I will explain in a few minutes. Report the mean to one more decimal place than the original data. Since the original data is reported in whole numbers, we're going to give 22.1 as our final answer. Another measure of central tendency, or to try to explain what's happening in the middle of the data, is the measure of the mode. The mode explains the most frequently occurring value in a set of data. The symbol we use for this is a capital M. So look at the data set below. What number appears more often than the others? If I look through here and I put them in order from least to greatest, here I have all the sets, the numbers rearranged from least to greatest, then I can see that I see the number 21 twice. None of the other numbers appear more than once. So my mode for this set of data is 21. What happens if I have more than one number that occurs the same amount of times? Then we call that a bimodal data set, which means that two numbers of equal frequency stand out. It is also possible that we have more than two numbers that have equal frequency. Then that's a multimodal data set. We have more than two numbers of equal frequency that stand out, then it's multimodal. So look at this set of numbers. I would like to determine the mode for these numbers that you see here. First, let's rearrange them from least to greatest. Oh, sorry. Nope, not rearranging them this time. We just look at them and we see that there are two 63s. So this set has a mode of 63. Determine the mode of this set of numbers. So I notice that I see two 63s, but I also see two 59s. And so they both occur twice. None of the other numbers occur twice, so this is bimodal. We have two modes here, 63 and 59. Look at this third set. What's the mode of this set of data? So I notice that I have two 63s, I have two 59s, and I also have two 48s. So this is an example of a multimodal set, two 63s, two 59s, and two 48s. There are three different modes in this set of data, and so this is multimodal. A median is another measure of central tendency. The median divides the data into two sets which contain an equal number of data values. It's the value that occurs in the very middle of the set of data that has been arranged in numerical order. For the median, you do need to go ahead and rearrange the numbers from least to greatest. The symbol we use is this X with a wavy sign across the top, and it's pronounced X tilde. As I said before, the median is the value that occurs in the middle of a set of data that has been arranged in numerical order. Look at this set. So the first thing we want to do is arrange the data in sequential order. Once in sequential order, the value that occurs in the middle of the set is the median. Now, if there's an odd number of data values, there is a single value that appears in the middle. So for example, here, our median is 21. It's exactly in the middle. However, if there is an odd number, if there is an even number of data values, then the middle falls in between two numbers. So the median is the average of the two values that occur in the middle of the data set. So we'll take the two numbers that are sharing the space in the middle, and we'll add them together and divide by 2. This one was easy. It's just the number between 21 and 23. However, sometimes you may have, when you line them up in order, a number like 15 and 47. You would still add the two together and divide by 2. Next, let's talk about variation. All of those things we just talked about the middle or central tendency. What does it tend to do in the middle of the set? We want to talk about variation now. How do my values vary from the middle? Are they all jumbled close to the middle, or are they all spread out from different distances from the mean or the median or the mode? Our first measure of data variation that I want to talk about is the range. The range is easy to find because it's the difference between the largest and the smallest values in the set of data. The symbol for range is R. Consider this data set. The smallest value the largest value is 44, and the smallest value is 3. So to find the range, I'm going to do 44 minus 3. Range equals 41. Standard deviation is another measure of data variation. The standard deviation is a measure of the spread of data values. A larger standard deviation indicates a wider spread from the central tendency than a smaller value for standard deviation. Let's look at the formula for standard deviation. I know this looks very complicated and large and scary, but we're going to break it down into several small parts to make it a little bit more manageable. This is a sigma notation. This is the lowercase sigma, a Greek letter of the alphabet, and we use that for standard deviation. Again, here's the sigma again. It means the same thing here, summing this difference after it's been squared. So we're going to add up all of these values, and then notice you see this capital N again, which still means the same thing. It means the size of the population. Note that this is the formula for the population standard deviation, which is a little bit different from the sample standard deviation. And so these are a little bit different. We're going to talk population now, and later in future lessons, we're going to differentiate and do sample standard deviation. Might be worth pausing the video right now and copying down these steps for calculating standard deviation so that you have them in your engineering notebook. I'm going to give you a chance to pause the video, and then I will, after you unpause, you will hear me explain what all of this means. Hopefully you have these written down in your notebook. This is the procedure for standard deviation. Again, we're going to break it down into smaller parts. First, we need to calculate the mean, which is given by this little mu signal here. This goes in this part of the formula right here. We need to know the mean for all of the data. Remember, to calculate the mean, you add up all of the points from the data set and you divide by the number of points. After we know the mean, we need to subtract the mean from each value and then square the difference. So this says take the mean away from every single x data point that you have, x data point minus whatever my average was, and then I'm going to square that number and write it down. After you have all of those differences squared, then we're going to take the sum of all of those numbers. So I'm going to write all of these. I'm going to take each data point, take away the average, square it, write it down. I'm going to do that for every single data point, and then once I have all of those values written down, this little e sigma right here means that I am going to sum all of those numbers up. That's step 3. After I have them all added together, we go to step 4, and I'm going to divide the summation by the number of values that I had. So then I take all that stuff that I just added up and I divide by however many points I had. And finally, your last step to calculate the standard deviation is take the square root of that number. Now I know that sounds really long and hard and complicated, but let's work through an example here real quick so that you can see how it's done. It's really not that hard if you break it down into steps. Again, there's a special note that we have about rounding in statistics. Don't round until the final answer. If you're writing the numbers down, you may round values, but keep them unrounded number in memory so that you can use it throughout the formula. We'll round at the very, very end. For standard deviation, let's round one more decimal place than the original data. So let's calculate the standard deviation for this data set. So here they all are. Step 1. Calculate the mean. So I'm going to add all of these numbers together, 524, and then I'm going to divide by the number of set points there are. And if I count each of these, then I find out there are 11. 524 divided by 11, 47.63 repeating. So I'm going to write this down, and I'm going to store this in my calculator's memory, the whole number, not just the decimal. Next, I need to take my mean, 47.63, and I'm going to subtract it from each value in my set, and then I'm going to square it. So I'm going to do 2 minus 47.3, and then I'm going to square it. I get this number you see on the screen. Next, 5 minus 47.63, and then square it. You get this number right here. Next, 48 minus 47.63, square it. I get this number right here. Next, 49 minus 47.63, square it. You get this number right here. Hopefully, you're starting to catch on. I'm going to click through the rest of the points so this video doesn't last forever. Some of you are probably thinking it already is. Oops, too far. So here are all of my data points. The data point minus the mean, squared it. Here's all of the numbers that I get. Remember in the steps I said write them down. Here they are, all written down. Step number 3 is add them all up. So I want to add all of those differences together. So I take all those numbers that I have written down, and I put them in my calculator. This is the number that I get. This is the sum of the unrounded squared differences, which represents the whole numerator, what all of this symbol represents. Here's the number that goes in that part of the formula right here. Now let's divide that number by the number of data values that we had. And we had 11 because I had to know that for calculating the mean. When I do 5,024 and this decimal divided by 11, I get 456.7769. So that represents everything inside the square root of this formula. So I have one more step to be able to find the standard deviation. Take the square root. So when I take the square root of 456.7769, I get 21.4, which when I look at my data set, 21.4 is actually kind of large because my range was from 2 to 63. 21 is almost half of that range. So this means that my data are spread all throughout that 2 through 63. If I were to get a smaller number, like say 2, then that would mean a lot of the data is centered around my mean because my standard deviation is not very much. So then we would know, even though my range is from 5 to 63, then if I got a small number for that standard deviation, whatever my average or middle number was, then most of my points are focused around that. And for right now, I think that's really all you need to know about the standard deviation. It's a way to tell us how much my values vary. And we'll go more in depth into this in future lessons. You have probably seen a histogram in your math classes, and probably even some of your science classes you've been asked to create one. A histogram is a common chart that's used to show the frequency with which specific values or values within ranges can occur. An engineer might use a histogram to show the variation of a dimension that exists among a group of parts that are intended to be identical. This is often the case, and this will be the case in the example of your puzzle cube. We might want to use a histogram to show how all of my 3/4 inch wooden blocks are supposed to be 0.75 inches by 0.75 inches by 0.75 inches, but after measuring you'll probably find that they're not. Large sets of data are often divided into limited number of groups. These number of groups are called class intervals. Notice here I have large set from -16 to 16. Instead of showing each individual value between there, we've broken them down into groups. -16 to -6, all of those will be in this bar. -5 to 5, all of those would be in this bar. And then 6 to 16, all of those would be in this bar. The number of data elements in each class is shown by the frequency, which is indicated along the y-axis of the graph. So -16 to 6 had about 5 data points. -5 to 5 had 7 data points. And 6 to 16 had about 3 data points. So let's make a histogram for this set of data. Here are my classifications. 1 to 5, 6 to 10, and 11 to 15. We're going to clump them to make this go faster. So how many numbers are between 1 and 5? Okay. So we are going to go from 0.5 to 5.5 because that's going to show 1 to 5. Any numbers that are in between there, so here is 1, 4, and 5, so it looks like there are 3. For 6, we're going to go 6 to 10. We are going to go from 5.5 to 10.5. For simplicity, we indicate only whole numbers since all of the data values fall within the intervals shown. Let's reorder the data to make it easier to divide into the ranges. Okay, the height of each bar in a histogram indicates the number of data elements or the frequency of occurrence within each range. So we've decided there are 3 numbers that are in between 0.5 and 5.5. The height of each bar is going to be representative of how many numbers are in that range. From 6 to 10, we have 4. And from 11 to 15, we have 2. And that's how your histogram is created. Note that you can always determine the number of data points in a data set from the histogram by adding the frequencies from all of the data ranges. If I needed to find the mean of all of these, I know that I have 3 plus 4 plus 2. I have 9 data points. This histogram represents the length of 27 nearly identical parts. The minimum measurement was 0.745 inches, and the maximum length measurement was 0.760 inches. Each data value between the minimum and maximum fall within one of the class intervals on the horizontal axis. Note in this case, each value indicated on the horizontal axis actually represents a class interval or a range of values. For instance, 0.745 represents the values 0.7445 to 0.7455. In general, the interval endpoint should have one more decimal place than the data values. Due to the precision of the measurement device, the data are recorded to the thousandth and will therefore correspond to one of the values shown on the axis. The bars are drawn to show the number of parts that have a length within each interval, the frequency of occurrence. For instance, if the 27 parts, 2 have a length of 0.746. and therefore will fall within the 0.7455 and 7465 class interval. 4 have a measured length of 0.750 and fall within the 0.7495 to 0.7505 class interval. Another way to represent this data is with a dot plot, and instead of drawing a bar, you just draw a dot for each instance, for each occurrence. So here's an example of the dot plot. There's one dot for each data point. Dot plots are easily changed into histograms by replacing the dots with bars of the appropriate height indicating the frequency. This is an example of normal distribution. In a later presentation, because this video is already way too long, we will talk about the distribution of the data. That is, we will look at how the data values are distributed among all the possible values of the variable. We will talk about a normal distribution or a bell curve, and that is what you see here. But again, that's a different video. Now, stay tuned for practice videos so we can practice finding that mean, median, and mode and standard deviation again, just for good measure.